Welcome. In this video, I'm going to go over solutions for section 2 in topic 2, starting with number 12, which says emission and absorption spectra both provide evidence for A, the existence of neutrons, B, the existence of isotopes, C, the existence of atomic energy levels, or D, the nuclear model of the atom. And scientists use emission absorption spectra to prove that energy can be used to move electrons around within the cloud, or C, the existence of atomic energy levels. Question number 13 says the diagram shows the lowest 5 electron energy levels in the hydrogen atom. Deduce how many different frequencies in the visible emission spectrum of atomic hydrogen would arise as a result of electron transitions between these levels. So what you're expected to know here is that any time an electron moves from an upper level to level 2, that would emit energy in the visible spectrum. So that means there would only be 3, even though there are more visible emissions available, they would have to come from level 6 or 7 down to level 2. So it's only when it drops to level 2 that we see the visible emission. Number 14, identify which of the following provide evidence to support the Bohr model of the hydrogen atom. The energy of the lines in the emission spectra of atomic hydrogen, that definitely supports the Bohr model. The energy of the missing lines in the absorption spectra of helium as seen from the sun. That doesn't help out because remember the Bohr model only supports a hydrogen atom, so helium's not going to help it out. And the relative intensity of the different spectral lines in the emission spectra, that also, even though there may be different intensities, it's not supporting the Bohr model. So the only one that actually supports the Bohr model is the first one, the energy of the lines in the emission spectra of atomic hydrogen. Number 15, list the 4D, 4F, 4P, and 4S atomic orbitals in order of increasing energy. And it doesn't matter if you're talking level 4 or level 3 or 5 or 6 or 7. It's always in the same order, and I always think of it as some poor, dumb fool. So S, P, D, and F would be the correct order. And 16, state the number of 4D, 4F, 4P, and 4F or 4S orbitals. And again, it doesn't matter if they're fourth energy level. D always has 5 orbitals, F has 7 orbitals, P has 3, and S has 1. Because if you start in the order, it's 1, 3, 5, 7. Number 17, apply the orbital diagram method to determine the electron configuration of calcium. So when you look at calcium, you have to realize that calcium has got 20 electrons. And on my key, I wasn't able to do the orbital diagrams. I did it as electron configuration. The difference is I'd write a 1s here, and then I'd show a box with the electrons in it. And then I'd go to the 2s and also the 2p. Because I know first, second, and third floor are full on calcium since it's a fourth period element. And then on to the 3s and the 3p. Oh, I shorted my p's over here by a bit. I need to have all 3 orbitals filled up. And my 3p then would have all 6 as well. And then finally, I come around to the 4s, and that too would be full to give me a total of 20. 18, deduce the number of unpaired electrons present in a phosphorus atom. So with 18, phosphorus I can see is number 15. It's energy level 3. So if I just think about its configuration is neon and then 3s2, 3p3. And what I can see is that since the p orbit is only half full, remembering Hund's rule or the bus rule, that means there'd be 1 in each of the p orbitals, or px, py, and pz would each have 1. So I'm going to have 3 unpaired. The only place I have to look for the unpaired orbitals should be the last orbital being filled. So here's where I would look for my unpaired orbitals, or unpaired electrons, I should say. Number 19, identify the sublevel that does not exist. There is a D, 5D, there's a 4D. 3F, however, does not exist. The third level has S, P, and D, but you have to be to the fourth level before the F shows up. Number 20, which is the correct order of orbital filling according to the Aufbau principle? And you will not have an Aufbau diagram. If you look in your data booklet, there's not one there, but you have your periodic table. So when you get down to the fourth energy level, you should see the 4s fills up, and then you should realize you go back to the D block, and you go back to the 3D block. Then you come back to the 4p, and then move down to the fifth energy level and the 5s. So C would be my correct choice. 21, state the full ground state configuration for the following elements. When they say full ground state, they mean not noble gas. So if they just say ground state, then you can use noble gas, but when it says full ground state, they're expecting the whole works. So VIC is number 23. I see it's the fourth energy, so 1s2, 2s2, 2p6, 3s2, 3p6, those are all full. Then I have 4s2, go back to 3d, and put the last 3 in there. And if I add up my electrons, I should come up with the 23 electrons that vanadium has. B, potassium, has 19, so it's going to be very similar, but I'm going to have 1s2, 2s2, 2p6, 3s2, 3p6 for those 3 full orbitals or electron energy levels, and then just 4s1 for the 19th and final electron. Selenium, Se, is number 34 and also a fourth level. So 1s2, 2s2, 2p6, 3s2, 3p6, and this time 4s2 is going to be filled. 3d10 will also be filled. And then 4p, I see there's 1, 2, 3, and 4 electrons. D, looking at strontium, I've got element 38, and now I'm down to the fifth energy level, so I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then I have to remember that 3d10 is in there, 4p6, and then finally 5s2. Number 22, determine the total number of electrons in d orbitals in a single iodine atom. Now this seems like a big deal to do, but if I find iodine, I see it's in period 5, and it's over in period 5, and it's in the p block. So what I know is that the d orbitals start up with the fourth energy level. You go back and fill up the 3d, and by the time I get to the p block on the fifth period, I've also filled up the 4d. So I have filled up a total of 10 d orbitals. I filled up the 3d, and I have filled up the 4d for a total of 10 orbitals, which means there's 20 electrons in d orbitals in any iodine atom. 23b, identify the excited state, not a ground state, for the following configuration. So basically you're looking for where the Aufbau diagram seems to have been disobeyed. 3s2, 3p3 seems correct. Ne would come around to the third floor. 3s2, 3p, I'm having trouble reading what that is. Let me just expand a little bit here. My copy's not so good. Looks like 3p3. It definitely isn't 3p6. So this appears to be my excited one because this p orbital isn't full. But I notice with C, 3s2, 3p6, that's good. 3s2, 3p6, 3d1, 4s2. This one also seems to be expanded. Oh, no, it's not. I'm sorry, they just put it out of order and fooled me because usually we write the 4s2, which fills up before the 3d one. So just B is in an excited state. And then number 24, deduce the number of unpaired electrons present in the ground state of a titanium atom. And if I find titanium, Ti, it's in the 4th energy level, so 4n, but it's in the D block. So that means my 4s2 should be full. So all I have to look at in the D block is how many go into the D orbital, and just 2 go into the D orbital, meaning both of those electrons are going to be unpaired. Number 25 says, state the full ground state electron configuration of the following ions. So with the first two, oxygen and chlorine, where they're gaining electrons, it's fairly easy to see how that changes the original or the neutral atom. Because with oxygen, I would have first floor is full, 1s2. Second floor, 2s2. Normally I'd have 2p4 for oxygen, so 2 more electrons, a -2 charge, would just mean that that p orbital is full, and I'm at 2p6, or a noble gas configuration. And then B is similar for Cl-. I've got 1s2, 2s2, 2p6, 3s2, and normally I have 3p5, but the -1 tells me it too has picked up an electron to become 3p6 or acquire a noble gas configuration. C and D are a little different when we get to titanium and copper because they're both transition metals. So the last orbital being filled, the 3D, is not the first to empty out. So when I look at it, I have 1s2, 2s2, 2p6, 3s2, 3p6, then I have 4s2, 3d2 is what happens with titanium. And so to become titanium 3+, it needs to give up 3 electrons. Well, the 4s, because it's further out, even though it fills up before the 3d, it empties out before the 3d. So I'm going to lose 2 from the 4s, and I'm going to lose 1 from the 3d. So my configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d1. Copper is going to undergo a similar change. This is a 4th energy level as well, 1s2, 2s2, 2p6, 3s2, 3p6, and then I get to 4s2, and typically I have 3d9, and so if it's going to lose 2, it's going to lose these two, the 4s2, and leave the 3d9 intact as it was. Number 26, state the electron configuration of the following transition metal ions by filling in the boxes. Use arrows to represent the electron spin. So Ti2+ is going to be very similar to Ti3+ we just had. It's still going to have 3D, but normally Ti has 4s2. Let me just write it over here. It's normally 4s2, 3d2. So if it's a 2+, it's these two that are gone, and there's going to be 2 spinning in 2 of the d orbitals. Fe2+ is normally 4s2, 3d, 2, 4, 6. So if I'm talking about, is that true? Is it 6, 2, 4, 6? Yeah, usually 3d6. So if it's Fe2+, it's going to have lost the 4s2, and I'm going to have 1, 2, 3, 4, 5, and one of these is going to become paired, which is why often we also see Fe3+, and that one paired orbital becomes unpaired like the other 4. Ni2+ is usually 4s2, 3d, 2, 4, 6, 8 for nickel, and it is lost 2, so it's the 4s2 that are gone. So that's going to leave me 1 in each, 6, 7, 8. And then zinc 2 plus is 4s2, 3d10, so losing the 4s2 would leave a full d orbital with 10 electrons. 27, state the full electron configuration for neon. So it is the noble gas on the second energy level, so 1s2, 2s2, 2p6 would be my full configuration. And B says state the formulas of two oppositely charged ions which have the same electron configuration as neon. So I'm going to take the easy way out. I'm going to go one higher and one lower. So fluorine would have, to gain an electron, F minus would become that same configuration. And the other option would be at the other end, Na could pick up one and become Na plus. Now, if you want to be more adventurous, you could have O picking up 2, or Mg losing 2, as well as having nitrogen gain 3, or aluminum lose 3. All 6 of those are possibilities. 28, use the periodic table to find the full ground state electron configuration of the following elements. It's getting a little old to do the full configurations, so I'm guessing by now some of you have quit doing these and might want to just skip to the next slide or the next set of problems. But chlorine again, A is going to be 1s2, 2s2, 2p6, 3s2, and just 3p5 since it's in family 7. And B, if I can find it here, number 41, niobium, is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and then finally I'm to 4d with just 3. And IB tends to write the 4D ahead of the 5S. That's how I did it on the key. It doesn't matter. They will accept it either way, so don't let it mess you up. C, germanium, is back in the 4th energy level, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10 since I make it all the way over to group 14, and then it is going to be 4p2 for germanium. And then finally D, SB, antimony, number 51. This could be a long one, 1s2, 2s2, 2p6. Third floor is 3s2, 3p6, then 4s2, 3d10, 4p6. And then I'm going to come around to 5s2, 4d10, and then finally 5p3. Number 29 says identify the elements which have the following ground state electron configurations. So any 3s2, 3p2, as I go across period 3, the 3s fills up, 3p2 would put me at silicon or Si. Letter B, argon, 3d5, 4s2. When I come around from argon, I have to realize that the 4s actually fills up, and then 3d5 would put me at Mn, or manganese. C, Kr5s2, I just count down to the 5th energy level, go over to the 2nd family, and I'm at Sr. And then D, they give me the full configuration, so 1s2, 2nd floor is full, S2P6, 3rd floor is full, S2P6, and then 4th floor, even though it says 3D1, 4s2, the 4s2 fills first, so 3d1 means I have left off at scandium or Sc. Number 30 is a weird question. It wants to know the total number of p orbitals containing one or more electrons in tin. Well, if I look at tin, tin is down in energy level 5, and it's in the second p group, so it's got 2 p orbitals from energy level 5. And then back in energy level 3, or energy level 4, it's filled up all the p orbitals, which is 3 of them. In energy level 3, it's filled up all 3. And in energy level 2, it filled up all 3. So when I add those up, it's 11 different p orbitals that each have 1 or more electrons. But it's not a total of 22 electrons. It's a total of just 20 electrons in the p orbitals, because 2 of those are unpaired. 31 is another odd question. It says, how many electrons are there in all the d orbitals in an atom of barium? So when you find barium, you see it's in family 246, so it's in 6s. And so that means on the 4th and 5th energy level, it filled up all the d orbitals, which would be a total of 20 electrons, because there's 5 d's on each of those floors. So 31 is also 20. Oops, got a little problem here. 32, state the electron configuration of the ion cadmium 2+. Well, cadmium, if I find it, CD is number 48. So typically cadmium is, and again, it says electron configuration, so this time I can use krypton and then come with 5s2, and then back to 4d10. So then the +2 lets me know the 5s2 would be lost, so it'd just be Kr 4d10. Question number 1 wants to know, what is the electron configuration of the Cr2+ ion? So I find chromium, and I see it's going to be argon, and then typically I would expect it to be 4s2, 3d4. So then if it loses 2, it's going to be the s2 that it loses, which would leave me with d, 3d4, and then they put the 4s0, which normally we would just drop it. Number 3, which is correct for the following regions of the electromagnetic spectrum? Ultraviolet, UV, high energy and short wavelength. Well, UV means it's on the violent end of things. So what you have to remember with Roy G. Biv is Roy G. Biv goes from the long and slow, low energy, to the shorter, I shouldn't say slow because they all move at the same speed, the shorter, higher energy at the violet end. So ultraviolet's going to be high energy and short wavelength, just like A is saying. But infrared's going to be off the other end, and it's going to be low energy, low frequency. So A actually is the correct pairing there. Number 4, an ion has electron configuration 1s2, 2s2, 2p6, 3s2, 3p6. So the 3 energy levels are filled. And then 3d10, which ion could it be? Well, 3d10 could be copper if it gave up 1 electron, so B would be true. Because if copper gives up 1, the other 4s1 would fill up the d10. Nickel giving up 2, that's not going to work. That's going to leave the 4s2, and it would just be 3d8. Copper 2 plus would leave it at 3d9. And cobalt 3 would actually leave it at d5. So the only one that's going to work there is B. Number 5, which best describes the visible emission spectrum of hydrogen? It's a series of lines converging at longer wavelength. That's not true because the lines converge by the purple, blue, teal, so that's the shorter wavelength. It's a series of regularly spaced lines. That's not true either. The red's kind of off to its side, and then they converge just like it says here, but unfortunately at the shorter wavelength. C, a series of lines converging at lower energy Or D, a series of lines converging at higher frequency. Well, A and C can't both be true. I mean, they either have to both be true or neither, because longer wavelength is lower energy. So D is my correct choice, a series of lines converging at a higher frequency. Number 9, in the emission spectrum of hydrogen, which electronic transition could produce a line in the visible region? So again, what you have to know is visible always comes to level 2, doesn't matter where from, so only B would be in the visible region. Number 13 is asking about the electron configuration of chromium. It says it can be expressed as argon 4sx 3dy, and explain what the square brackets around argon represent. They represent the inner electrons, or the first 18 electrons that don't get involved in too much. Then it says state the values of x and y, and what they're getting at is typically we would assume it's 4s2, 3d4, but what scientists have found is that this takes more energy than if this electron, I wanted the eraser there, if this paired electron splits up and leaves the 4s and the 3d all half filled. So x is actually going to be 1 and y is going to be 5. And then C says annotate the diagram below showing the 4s and 3d orbitals using plus and minus. I'm going to have all my arrows pointing either up or down. They're all going to have the same spin for the least amount of energy. And number 14, annotate the diagram below showing the 4s and 3d orbitals for a copper 2+ ion using up and down arrows to represent a spinning electron. So copper 2+, typically I would think of it as 4s2, 3d9, but like chromium, the reality is that it's actually 4s1, 3d10. So if it's copper 2+, it's going to lose the 4s1 and leave me with the 3d9. So I'd have one each going up, and then 4 of these would be paired up with the 4s empty and the 3d having 4 out of the 5 d orbitals being paired up.